Hi, everyone, and welcome to another episode of Pathfinder, a podcast by Payload, the leading digital media company in the space industry. I'm your host, Mo Islam, and today we're joined by Ed Mehr, the co-founder and CEO of Machina Labs, a company building the next generation of factories by combining advances in robotics and AI. Today, we talk about the state of manufacturing in the US and how Machina's technology enables rapid iteration and production, a lot faster than traditional processes. And before we jump in, a brief word from our sponsors. SpiderOak's Orbit Secure software is designed for hybrid space operators struggling to manage the chaos of securing data flow and access to and from tens of thousands of small satellites in low Earth orbit. Using a unique combination of end-to-end zero-trust encryption and blockchain distributed ledger, Orbit Secure allows your mission to orchestrate and secure Earth-to-orbit, orbit-to-Earth transmission, communication, and storage of sensitive data across even the most complex and unsecure hybrid space environments. To learn how Orbit Secure can bring zero-trust security and resiliency to your zero-gravity environments, check out SpiderOak at www.spideroak.com. Ed, welcome to the show.
Thanks for having me.
Yeah, where are you sitting right now?
I am right now.
Banging.
Yes, we're sitting right above our shop floor. So we are in Chatsworth, California, in one of our conference rooms. Downstairs is the shop floor. We have a 36,000 square foot facility down here. We have deployed 24 robots right now downstairs. So sometimes you might hear a little bit of noise and something banging at something else, but we're just right above the shop floor.
If you're building an advanced manufacturing facility and we didn't hear banging, I feel like we'd be worried.
That's right. Especially if you're like making big parts in our cells. I don't know if people have seen it. They're like, 30 foot by 30 foot, and they're a behemoth. They're like 16 feet tall and 30 foot by 30 foot manufacturing.
Exactly.
Cells.
All right. Well, let's start from the beginning. Tell us, you've had a really interesting career. Before we jump right into that, give us a little bit of, Machina Labs. What is it? What are you guys building?
Yeah. So at Machina, we were working on next generation of manufacturing floors. And by that, I mean manufacturing floors that are flexible, meaning that you can change your design, you can change your material without having to change your factory. And the main enablers are robotics and AI. So we are building a manufacturing cell that we call Robotic Craftsman. It's a manufacturing cell that uses robotics to have the dexterity of a craftsman, but also have the software and the machine learning and the AI piece that replicates what's happening in the mind of the craftsman. So you get that flexibility. You can change your material, you can change your design just through changing software without having to change any tooling, any hardware in the factory, and do another part without investment in CapEx. And we think this is going to be the core tenets for next generation of manufacturing floors.
So, Ed, when we first met, you brought up an example that I think really brought it home for me, at least someone who spends so much time in the space industry. Because you talked about the Falcon 9, you talked about how the Falcon 9, right now, if SpaceX wanted to increase the height of Falcon 9, they could do so with relative ease, but changing the diameter of the rocket body is far more complex. If I got that right, tell me a little bit about why what you're building solves that problem.
Yeah. So the problem you mentioned it's only specific to SpaceX. It's a general manufacturing problem, meaning that most of the shop floors, most of the factories are built very specifically for the type of parts you're trying to manufacture. For example, when you want it, in Falcon 9's case, when you want to build a tank, a launch vehicle's tank, you have to pretty much build molds that are specifically built for that diameter of the tank, right? In specific cases of a Falcon 9 is that, all the tooling and all the molds and all the dies that are specifically built for that size of the diameter from the tank all the way to the fairing are specifically built for that. They're constant. The moment your design goes to the point where you need to change that diameter, you have to reinvest in those tooling. And that's a huge investment. If you look at Falcon 9, Falcon in general over its lifetime started from a shorter height and keep getting taller, but the diameter of the vehicle is much harder to change. And as a matter of fact, I think on their new vehicle, which is a Starship, which has recently had a successful test on the second flight, they had to start from scratch in another facility. A lot of that development and manufacturing is being done out in Texas. The tooling that's used for Falcon 9 doesn't necessarily applies to Starship. And that's a common problem. It's not just specific to aerospace. It's not just specific to SpaceX. It's a common manufacturing problems. Every factory, for the most part, is built specifically for the type of part, the type of material you're using. And it's very hard to change it if your material or your geometry is changing.
So what is your key product offering today that enables companies to actually solve that problem?
Yeah. So when I was at SpaceX, I think this is a little bit of a journey. When I was at SpaceX, saw that challenge, I got really excited about 3D printing, right? 3D printing is one of those solutions where kind of promised that geometry agnostic, material agnostic part manufacturing solution, meaning that you could just upload a CAD and you can make another part and you don't have to invest in a new factory. So that's what kind of propelled me and excited me about joining Relativity in early days, Relativity Space, and working on working on Stargate, which is the name of the large envelope 3D printer that Relativity Space is developing. But going through the work that we did at Relativity, I realized there's a whole array of parts that are not necessarily amenable or accessible to 3D printing. 3D printing is great. It's a very good process to be, geometry agnostic and material agnostic. But the type of parts that we do in manufacturing are so varied, and there are so many parts that you cannot easily, either it's not feasible to manufacture it in terms of physics using 3D printing, or it's just not economical. So we started Machina focusing on biggest sector of metal processing, which is sheet metal forming. Today, if you want to get a form sheet metal part, and by form sheet metal part, think of tank dome, or you can think of an automotive car door, a side panel of a car, think of a wing of an aircraft. If you want to get a formed sheet metal part, you have to basically invest in a lot of money in tooling and dies specifically for that part. So we started Machina to first address that market. How can we get rid of that die? How can we form sheet metal parts without having to invest in a die? So we developed a process called roboforming, which is basically like two robots working together to form a sheet of metal from scratch, from a flat sheet all the way into complex geometries, the same way a potter forms a clay bowl. If you've seen how the potter works, start with a lump of clay, and it pinches it and deforms the lump of clay, for example, into a bowl. We're doing the same thing to a sheet of metal. The process is very similar, except the forces are much higher. We're deforming a sheet of metal that's just much more stronger compared to a clay bowl.
And how did you come up with this idea? Like, what enabled you? I assume it was while you were at Relativity working on Stargate.
No, actually, I think the idea of forming the way we are doing has existed in academia since 1970s, right? And some of the folks who have been doing research on this are actually advisor to our company at the moment. So it's definitely not a new concept. There are enablers which we deployed that overcome some of the remaining challenges before we can commercialize it in terms of cost, in terms of accuracy, and we can talk about that more. But the manufacturing process itself had been researched mostly in academia from, like I said, 1970s, 1980s. Some of the companies like Boeing and Ford have been doing some research in this area, but nobody has successfully commercialized it. And we have that few key ingredients needed to commercialize it and kind of overcome those challenges that research hasn't been able to solve.
Well, let's actually talk about that for a second, right? So you said a number of businesses have tried this and it hasn't worked out. What are sort of the major advancements that you and your team have made that has allowed you to actually create a business model out of this?
Yeah. So there are multiple challenges, both technical, but also from business model and economical viability. So the technical piece has been mostly around accuracy. How do you get accuracy out of the parts formed this way, right? So that's one of the challenges. I'm going to talk about it. And then the other piece is, how do you make sure the system is cost effective enough so that it makes sense for somebody to buy it and manufacture parts. And the last piece is, how does this integrate with the rest of manufacturing processes, right? As you know, manufacturing is very vertically integrated process. Each part needs to go through multiple processes. So even if you solve one problem in the chain of all the processes, or remove one bottleneck in the chain of all the processes needed to make a part, you might not necessarily be able to take the economical benefit and advantages at the end of the day if other parts of the process is still, have bottlenecks, or they cannot keep up with the new improvements. On the first technical challenge, how do you improve accuracy? We brought in empirical modeling, right? So the traditional approach has been you simulate using FEA, using physics-based modeling. You simulate what happens to a sheet of metal through a process like we have, and then use that simulation to come up with the right process parameters to form an accurate part. The challenge with simulation, as a lot of people in the aerospace world know, is that they're not accurate, and they also take a long time. So, for example, a part that we can form in a couple of hours or even half an hour will take a week to simulate on a 27-core machine today, right? And at the end of the day, the simulation is not very accurate. So it hasn't been a viable way to iterate on the process and generate proper process parameters. So instead, we kind of flipped that on its head and said, okay, what if we created a manufacturing process or a manufacturing system that constantly can generate data as it's forming parts? And then we use those data to build models that are not necessarily physics-based. They are empirical, machine learning-based, AI-based models. And they use those models to come up with the right process parameters to get to the right accuracy. So, and this has been only possible due to recent development on AI and ML, but also bring the cost of developing some of these systems down to the point where you can have a system that's cost-effective enough and can produce a lot of data, so you can use those data to build those models. And the second piece was, how do you build a system that's cost effective? That's why we started looking into off-the-shelf robotics, right? Robotics have been, for the past 50, 60, 70 years, have been in manufacturing environments, right? Since 60s, we have seen robotics in automotive manufacturing environment. So the robots itself, they have been matured and become a commoditized product in the past 60, 70 years, to the point that, you have multiple manufacturers manufacturing similar type of robots. So when you're starting building a system, if you could use and take advantage of these off-the-shelf robotic system, you can significantly reduce the cost, as opposed to making a bespoke, from ground up, develop your own hardware, and kind of not taking advantage of the costs that have been improved over these years. So we introduced robotic and off-the-shelf sensors in building these systems. But then the nice side benefit of using robotics was that we also helped solving the next piece of the puzzle, which was, how does this integrate with the rest of the processes? By using a robotic system, we can easily develop different types of processes into our manufacturing cell. So we call our manufacturing cell a Robotic Craftsman. And by that, we mean that you can form the parts with it, but then you can drop the forming end effector, pick up a scanner, scan the parts, so you can do QA within the same system, but then maybe drop the scanner, pick up a surface finishing end effector, does surface finishing, drop it, pick up a welder, and maybe do additive features or join different parts of the of your product together. It allows you that flexibility to integrate downstream processes to actually enable go from feedstock all the way to the final part without having to interface with traditional manufacturing equipment, right? And we call that whole system a Robotic Craftsman system. So those are kind of the three main enablers. There's a bunch of other things that we did at the company, but those are the three main enablers that allows us to kind of take this research project out to the industry and commercialize it, right? Improve the accuracy using AI ML, use robotics to bring the cost down, but also think about it holistically. How can we have a platform that can take the part all the way from feedstock to the final part?
I want to take a quick step back and just ask a bit of more of a macro question. So when you look at the state of manufacturing in the United States today, outside of cost reduction, which is obviously the headline thing that you're allowing, companies to do, right? I think you told me once that, building one of these existing machines to do sheet metal forming and pressing are very, very, very expensive, and they're very custom. And if you needed to, change a little thing, it takes weeks to re-engineer the machine to be able to do that. So like clearly, cost is a significant piece of it. But when you think of the state of manufacturing in the US, like why is this so important?
Yeah. So obviously we all know we had a problem. The main problem we have in manufacturing is that manufacturing doesn't exist in the United States. I mean, in aerospace defense, we have some of that, but dominantly the manufacturing moved out of United States. And the reason for it is actually, if you do like a 5 why analysis and kind of try to get to the root cause of it, is the technology, right? Technology limitations. When you have a process that cannot easily change, and that's most of the manufacturing process, when you have to build a factory very specifically for each part, what ends up happening is that factory needs to manufacture enough of the same part to be economical. You talked about cost of for example, a stamping facility. If you look at Tesla's press releases for Gigafactory in Austin, they spent $150 million on a stamping facility. And every die for Model 3's side panel, it costs them $1.5 million to make. And that's a die specifically to that geometry, specifically to that material, meaning that tomorrow, if you wanted to go from Model 3 to another design, you have to remake that die. So it's another $1.5 million investment. So as a whole, manufacturing, the main problem it had, and that's the underlying technology, is it's just not flexible. The technologies we use today in manufacturing are not flexible. You cannot change your design. You cannot change your material easily. And if you have a factory that's not flexible, you have to invest a lot of money in it. What ends up happening is you have to make sure it makes enough parts to pay for itself, meaning that it needs to centralize and make parts for the rest of the world, right? Where would you centralize it? You would centralize it in Southeast Asia, in areas of cheap labor. Now, we did that, a few decades ago, and now we realized, okay, we lost that capability. We exported it to other places, but now we're dependent on those areas geopolitically, and it's creating these geopolitical instabilities that we see today, right? So, in order to bring manufacturing back to the United States, we need to solve that core problem. The core problem is, can you make the factories more flexible, not rigid? And that means that we need to invest a lot in these new type of technologies that are more flexible, because if you go back and try to bring those inflexible manufacturing back, we're gonna have the same problem. The labor is going to be more expensive, and those factories by nature lend themselves to centralization, because what we talked about. So I think because of that core problem, the next generation of shop floors need to, at core, solve this flexibility problem. Can we make manufacturing flexible so that one day they can make automotive parts, the next day they can make aerospace parts? Right. If you solve that problem, we can truly democratize and decentralize manufacturing.
So going back to your business, you mentioned that the one part that's easily commoditized or that you don't really have any need to build yourself are the actual robots themselves, right? So how do you think about the moat around your business, right? If you're acquiring the robots that are themselves doing the work, like what is the key moat around the business?
Yeah. So the key moat is in two things. One is in the software, right? So these robots are, you can buy these robots and they will do what you tell them to do, more or less. But what you do with the robots is the key moat, right? And we talked about basically, if somebody buys 2 robots and try to do our process with the very first, most heuristic way that they can think of, you will end up getting a part that's like inches off of the design and usually tears, right? So the main problem, we talked about accuracy piece, that's comes down to what process parameters, how do you basically command robots to do different operations so they can actually get the right parts. And that's enabled by data, right? The more parts we form, the more data we gather, and we can use that data to come up with the right process parameters to make the right part. So I would say 70 or 80% of our IP is in that software piece. But also we have to design a lot around the robots in terms of hardware as well, right? The end effector, the forming end effector, the clamping frame. So all of those are also proprietary design by Machina Labs. And it's the forming end effector is important because you need to have something that can last forming many parts, and what is the material that we're using? What is the coating that you use there? Those are also part of our IP, but I would say 80% is really in the intelligence of the system and replicating the mind of the craftsman, which comes from the data. And if we only have the data and nobody else have it, we have a huge moat there. And the more we manufacture, the more we know how to manufacture these parts.
You mentioned the Falcon 9 issue was obviously not specific to aerospace, but it can be applied to a lot of different industries. What are the industries that you're focusing on right now, and how are you thinking of expanding that customer set over the next, call it, 5 to 10 years?
Yeah. So we have seen a lot of traction between different aerospace and defense companies. One area that, I never thought about it initially, and now we have the most traction with, has been sustainment, or MRO, or aftermarket. We talked about factories being inflexible. Think about how are they going to support, 10, 20, 30 years of spare parts after the production is done, right? If you have one factory that can make one part over and over again, it cannot be making it for 40, 50 years after the product is discontinued production. But it does require 50, 40, 30, 40, 50 years of spare parts to support that that vehicle. Think of, United States Air Force right now has a variety of vehicles that are flying from 30, 40 years ago, and they're still supporting these aircrafts. So one of the areas that we soon saw a lot of traction was in sustainment. Can we manufacture spare parts in a much more economical, faster way? There are parts on our military assets today that have 4-year lead time, meaning that if it gets damaged, that asset needs to stay on the ground for 4 years before it can get a spare part. And these are not complicated spare parts. You can think of landing gear door, skin of an aircraft. But because the production has ended, sustaining these and remanufacturing has become a huge challenge. So that's one area that we have seen a significant amount of traction, and we're working with DoD on that. And then the other area that also kind of surprised me, and we have very good amount of traction with, is on composite molds. When I started this business, I never thought that, we're going to get in close to composites or anything related to composites. I always was thinking about sheet metal. But traditionally, if you make a composite mold, you have to first manufacture a mold. These molds are usually machined, meaning that, if you, for example, think of a wing of an aircraft, you have to go make a very giant mold by machining a giant billet of material to the shape of that wing. And then you lay up composite on top of that. You vacuum bag it, you put it in an oven, for example, if you're doing an autoclave process, and then cure it and you get a part. Now, that mold for that wing is actually a bottleneck. Machining that giant wing mold takes a long time, but also it's very wasteful. And a lot of time you're doing on a very expensive alloy like Invar. So it's a huge bottleneck, both in terms of cost and time to get to a part. Now industries are thinking about developing 6, 7, 8 different, for example, eVTOLs or drones. That means you have to go through a whole bunch of these sets of these molds to manufacture and develop those vehicles. Not easy to do. So they actually came to us and said, can you form a mold? Traditionally, sheet metal was not available to mold making business because you needed a mold to form a sheet metal part. But now with our process, you don't need that. So you can actually go ahead and make the mold right from the CAD and design. So that has been also another area of a lot of interest. We have multiple contracts, both with the government and some of the commercial entities on that. I think, and the last piece, which I wanted to kind of talk a little bit about, was enabling something that were not possible before. We have seen, a lot of alloys that traditionally are not stampable, or you cannot form them in a traditional sense. We can actually form them because we have more control over the process. Think of titanium. Titanium is traditionally very hard to form, but it has a lot of applications in hypersonics, for example. So if you can process these alloys and form these alloys in a better way, that's very, very attractive. And so those are the third category of things that we're doing, enabling alloys that traditionally were not possible. But now with our process, we can actually form and process them.
It's funny you say that. I had titanium and Inconel on my list of alloys to ask you about, but it sounds like you guys are already down that road.
Yes, both of them. Yeah, titanium was a big surprise. It's a huge demand for it. We talk about SR-71 being built out of titanium, so a lot of folks in hypersonic space are looking into that. But Inconel as well, high temperature alloy, traditionally not being formed, can we form them? So both of those are on our radar.
So let's talk really quickly about the business model. Both on the commercial side and the government side, how are customers working with you? Is it like, hey, we need this part, can you please build it for us? Or like, hey, give us the stack, we're going to incorporate it into our factory, and we're going to be able to utilize your software to be able to build what we need to build?
Yeah, we work with customers in both ways, right? Usually the interaction starts from, can you build a part, right? And that's kind of a Pathfinder, right? So we start with manufacturing parts in our facility. And then once we get to the point where, they feel good about that part, then the discussion becomes, how can we get this in higher volume? So a lot of time it makes sense for us to deploy our manufacturing cell to their facility, or potentially continue to manufacture here on site for them and, have a dedicated capacity for them. And it also depends on the, how big the customer is. But like with a lot of startups, they don't have the capacity to integrate a new manufacturing cell, but they want us to make parts for them. For somebody like Department of Defense, which has huge manufacturing capacity, we are integrating ourselves. So we do both business models, manufacturing parts, and also leasing our cells or selling a subscription to our cell that will be deployed in the customer facility to make parts for them.
So what do you think ultimately? Do you think over time you will continue to do both? Or do you think that there will be a part of the business that will overshadow the other in terms of whether you're you're building this like juggernaut machining or, factory effectively, manufacturing facility? Or do you see a lighter model?
Yeah. I think both model will exist to some extent. There are applications we're discussing right now that, we have to deploy, right? It's on the edge. So think about sustainment application where, you have vehicles and systems that are all around the world and need to be repaired right where that vehicle is. So it makes sense for our cell to be very close to that. But I think as the technology becomes more widespread, I think the model that will win out eventually is very similar to how data centers operate, right? We're going to have facilities around the world where each of these facilities have, 100, 200, 300 of these manufacturing cells. There's going to be a, kind of portal where the customer can just log into and say, okay, here's my design. That design guide the customer through how to make that design manufacturable. And then the customer says, okay, I want, 200 of these here in Hawthorne in a month. And then right facility near Hawthorne will be programmed to manufacture those 200 parts and send it to them. And this become even more of a reality when each of these cells can do multiple operations, right? Where you can now break a part into forming, maybe then welding, maybe then hole making and trimming, and then assembly, and then you can program the right number of cells to do the right mix of operations. So I do think eventually in long term, we're going to see a model very similar to data centers, where we're going to have facilities with a lot of manufacturing cells in them, with a portal, with an interface that's online, and it can be programmed remotely to do different types of operations.
Right. Ed, let's take a quick break, but when we come back, we'll have a lot more to talk about. So stay with us. Space is the new frontier for cybersecurity. To quote the commander of the U.S. Space Force's Operations Command, cyber threats are unfortunately the soft underbelly of our global space networks. SpiderOak, the leader in space cybersecurity software, is dedicated to providing space operators with the solutions they need to protect hybrid space systems. Their Orbit Secure software uses a unique combination of end-to-end zero-trust encryption and blockchain distributed ledger, allowing missions to orchestrate and secure Earth-to-orbit, orbit-to-Earth transmission, communication, and storage of sensitive data across even the most complex and unsecure LEO and hybrid space systems. To learn how Orbit Secure can bring zero-trust security and resiliency to your zero-gravity environments, check out SpiderOak at www.spideroak.com. So this is not my favorite question to ask, but I do want to ask it because I'm curious how you think about it. But how do you measure your market? What is the size of the market?
Yeah, it is a tough question. Not because it's not measurable. I think if you look at forming sheet metal, it's a pretty huge market. like I said, it's the biggest metal processing sector out of all. It's a $250 billion market overall. But, what portion of that market kind of specifically applies to us? That's a different question, right? I think for our entry point, we're starting to look at applications where designed, the number of parts per design is below 1,000. Because we can easily change design and switch design, I think that was the perfect fit for us. Even though theoretically, the break-even point can be pretty high. We talked about, a stamping facility costing $150 million. If you invest $150 million in our technology in the same spatial footprint, the break-even point in terms of throughput is very similar. But it made sense for us to start going after low volume and high mix, which means a lot of aerospace defense, agricultural, heavy machinery. We're talking about, low volume, luxury, maybe automobile and cars. And we started looking to size that market. We started looking at their alternative processes. What processes do they use today? And what is the size of those market? What is the size of a hydroforming market? What is the size of a superplastic forming market? Low volume sheet forming processes. And that got us to around something around 20 to 50 billion, depending on how you count it. Now, that is the size of today's existing market. I think there is an opportunity for that market to significantly expand. When we were at SpaceX, the mechanical engineers were actively discouraged on making formed sheet metal parts because it would take such a long time. By the time you were done getting your first batch of parts, your requirements might have changed. So people would design around it and would not use sheet metal forming. With us, when the timeline goes down to hours of kind of iteration, then that dynamic changes. So I think the market also will significantly expand. That's the piece that's much harder to predict.
So let's talk real quick about the team. How large is the team, and how's it structured?
Yeah, so today we're around 60 people. We're planning to double our size and get close to 150 in the next 2 years. Biggest portion of the team is engineering. We have, fortunately or unfortunately, we have to be very multidisciplinary. As you can imagine, there is different types of engineering involved. Like we have robotics team, we have our ML team, MLAI team, we have our software team, which builds like applications and software that allows us to prepare geometries for our process. We have our mechanical engineering team, which makes end effectors and integrate the robotic system. So very multidisciplinary team on the engineering side is our biggest team. But we also have our production team, which is basically uses what the engineering team manufactured and produced to make parts for the customers or replicate development and manufacturing of the cell, the robotic cell. We also have our product team. We are a matrix organization. Because we are very multidisciplinary, we use product managers to kind of gather different folks from different disciplines to make different features for our systems. And we have an operations team that supports HR, finance, and then obviously sales and business development and application partnership team that works with our customers to identify applications and meets their needs. So
you recently raised a pretty significant Series B, $32 million. One of the investors that stands out to me is Nvidia. Tell us a little bit about that partnership. Why did Nvidia find this so interesting?
Yeah, so I think Nvidia was a great partner for us. Like I said, one of their biggest moats, what enables this application is modeling, capturing data and building process models using empirical data that allows us to come up with the right way of making the parts with accuracy. And obviously, NVIDIA has a huge legacy in that world. So I think they saw that the next generation manufacturing floors require data and empirical modeling. So they saw that opportunity and they agreed with us. And that's why we kind of joined forces in this next round. Yeah, we're excited to get their help on kind of improving and upping our ML and modeling capability. Also, their GPUs are deployed in our manufacturing cells. So a lot of computation that we do on the edge on the manufacturing cell is done with GPUs. So I believe, and I don't know this for fact, but I believe one angle is like, how can you How can you expand into different markets that maybe potentially Nvidia didn't exist before, specifically manufacturing? Can we deploy their GPUs into shop floors and be used in the manufacturing floors itself in the process computation for different manufacturing processes?
Right. Now, as a former SpaceXer, I have to ask about Elon's algorithm. So Elon consistently talks about how much harder and difficult building in an efficient and scalable manufacturing process is versus initial R&D and design, right? I've heard him talk about this multiple times. He just can't emphasize enough how difficult it is to build a manufacturing process. So obviously, as you know, he has, Elon has his own algorithm on manufacturing, questioning requirements, deleting unnecessary processes, using automation, but not, sometimes it doesn't make sense to automate everything, right? So from your perspective, having lived that world and now obviously building and trying to help companies build more scalable, efficient manufacturing processes, what are common mistakes that you find startups making that can be avoided?
Yeah, I think number one, on the startup front, I think number one is really, and it's a common mistakes, build it and they will come. Is also common in manufacturing. People get excited about a specific process and they really want to develop it because it just feels cool and it's a great tech and it's cool tech. But having that customer early on involved is pretty important. I think one thing we realized is that, and I really didn't want to do it, is never kind of lock yourself out, go into a lab and build something. Start with the customer geometry, start with the customer need, and then build around it. So I think that is not only manufacturing space. Obviously, it's a device that probably applies to most companies. We had revenue since day one, and I think that's a pretty important thing, both in terms of motivating the team, but also making sure you're building the right product to do it. But I think you brought up Elon and kind of that fundamental thinking in terms of simplifying requirements and asking questions about a requirement. I think that was what enabled us to start thinking about this problem, right? Why does manufacturing need to require a die? Why is the cost so high? Why everything needs to be built very custom and specific? And can we do it a better way? And as long as you can basically get to a point where you can devise a system or a product that's 10 times better. That was another thing that we learned, when we were at SpaceX. Once you can devise a solution that's 10 times better, then it's worth spending time into it. Right? If it's only marginally improved, if it's 1 time, 2 times, 3 times better, then it's just really hard to build a business around it because these manufacturing businesses are really tough. There's a lot of things can go wrong. So you need to make sure you have a whole lot of room for improvement so that it counts for all the mistakes you might make along the way. And the impact in the end is large enough where, you're not going to get bogged down and you're not going to kind of get derailed by simple mistakes that you will inevitably make along the way.
How do you think about competition in your space, right? Because in a way, you're dealing with traditional manufacturing processes. And if you're talking about the large, for example, automakers, right, they're probably fairly set in the way that they've been doing business. So is that sort of are those customers potentially not accessible or will take time to, break into sort of their processes versus working with a startup who's obviously starting from the ground up and there's clearly ways that you can, enable them to think differently from day one. So how do you think about that and how do you think about competition?
Yeah. So I think this is a very, very important question. It's probably the most important questions on, business development side, right? What is our go-to-market? How do we make sure we can deliver a solution that make a change and it's adopted by the customers? Certainly there's certain type of customers that are earlier adopters than others. For example, automotive is usually not an early adopter because they have to spend the past 40, 50 years really fine-tuning their supply chain and basically fixing the processes and fine-tuning how they can squeeze the most amount of efficiency in each step of the process. This is very hard for them. It's a very well-run machine. It's very hard for them to pick something out and replace it with something else in that supply chain that's super highly optimized. So you need to figure out who is your early adopters. Hopefully your early adopters are not just the startups because the startups have their own problems, right? You don't want to, as a startup, if you're working with other startup, it's not only just the risk of adoption and the technology, but the risk of their existence. Would they got to be pull off the value they're trying to deliver to their customers so that you can also get there? So it's very tough. So I think early days, you need to figure out the right mix of customers that is an early adopter. In our case, early adopters care about lead time, right? Can they get their parts faster? It's not about cost necessarily yet. It's mostly about either a lead time, how fast can they get their parts, or do something that was traditionally impossible to do. And hopefully you can find somebody, startups are great, but hopefully you can find a customer that also doesn't have other risks, it doesn't have an existential risk like a startups, right? So hopefully you can find somebody in the industrial world with enough stability to kind of invest with you and partner with you. So we found that, obviously with DoD, with some of the aerospace companies that are more mature. But then, I think as the product matures and develops, then, automotive might be your second stage adopter, and third stage adopter might be maybe construction or industries that are even much later adopter to these type of new technologies. The other piece I think I would add there is you also need to think about what is the scope of your business. We can thought about our business. We talked about business models. We could be a part manufacturer. We could be a system supplier. Or we could be a even bigger than that application provider, manufacturing solution provider. That's when, that's the category of, for example, not just making a face sheet with a mold, making an actual composite mold and everything that's needed for it. So you need to also start thinking about where do you want to draw the line so they can actually convince and deliver value for the customer. So that's another piece that you have to discuss internally. Where does your product end in early days? And that might be different than 5 years from now.
Well, let's actually go 10 to 20 years from now, right? Like just pressing on that point. In 10 to 20 years, what is Machina's place in the manufacturing ecosystem?
There's going to be a significant change in manufacturing. I mean, all the wins are, in our sail in terms of reshoring, in terms of AI is in a good place. Robotics is in a good place. I think it's ripe that in the next 20 years, manufacturing turns into a fully automated kind of platform. I really think what happened to the IT industry needs to happen in manufacturing. And by that, I mean the invention of the data center. If you were back in 1980s and you wanted to deploy a new software, you pretty much had to go build a data center to host and serve your software. And that's why only IBMs of the world existed in that paradigm. The reason we had this massive explosion of innovation in the IT industry really is that by decoupling the infrastructure from the ideas. Today, if you want to build a software, you can basically go to AWS and Azure and scale your process. You start from one server that you can rent from them and put your idea on it, all the way to thousands and millions of servers, a matter of seconds, and that really democratized that world in terms of ideas. All these apps came about, the development of machine learning models and these large language models were enabled, right? A lot of them are built on these giant flexible infrastructure like Azure and AWS. So I think we need to make that happen in manufacturing as well. So I think Machina can be that infrastructure. And I'm thinking about a flexible manufacturing infrastructure that completely abstract away the manufacturing from design and ideas, where somebody with a great idea can log into a portal, design their part, and submit it to manufacturing, and the right manufacturing facility that has the right number of our cells that can do multiple operations can be programmed to do different things to manufacture that part. And the designer doesn't have to think about building a factory, right? I think, and that's the future that I think in 10 to 20 years we're going to have.
That's a very exciting future is what I should say. And obviously there is a huge movement towards onshoring and reshoring production capability. So, and for us, like labor is a big problem, right? We don't have the skilled labor that other countries do. So our only solution is automation and basically a lot of what you're mentioning. I want to go back to a little bit of your history. As one of the key people who scaled additive manufacturing for the space industry, how do you see that technology evolving over the next decade?
Yeah. So additive is going to be a big component of next generation manufacturing floors. But the way I think about additive is that it's one of the tools in our tool belt. So I think there's a lot of good companies like Freeform, like Falcon, who are working on increasing some of the limitations that additive has today in terms of process throughput and the speed of making parts. But at the end of the day, I think we got to move away from the mentality that additive, this, one solution to solve all of our problems. I think we had a little bit of that mentality in the past few years where everything was a hammer, everything was a nail, and additive was the hammer. I think the next generation would be a combination of a bunch of agile processes. And additive is going to be a big component to that. There are certain parts that are more amenable to additive. There are certain more parts that are amenable to subtractive and CNC, and there are certain more parts that might be formative parts, right, where we are trying to tackle. So I think the next generation is going to be hybrid processes, right? They're going to be systems that can do multiple processes, either be additive, subtractive, or formative, or downstream processes like assembly and joining. We need to use the right tool for the right part, and I think we're going to see that in the next few years.
Are there any manufacturing technologies that you're particularly excited about that someone else is building, not you?
Yeah, so I think there is there's a lot of work being done on friction stir welding right now, but then additive friction stir friction stir additive. And
break that down for us.
They're getting very good properties.
Break that down for us for the non-manufacturing folks.
Yeah. So some of the folks who've been in SpaceX are familiar with this process. So there is you can, when you're joining two parts, you can use welding techniques. Most of the welding techniques rely on heat. Basically, they melt the material and then you create a melt pool, you connect the material, and then it solidifies. There are few cold welding processes, meaning that the part does not fully melt. And friction stir welding is one of them, where you rub a material on another surface in a very high speed, and the frictions from that process basically reduces gets material closer to this melting point, and then they join. And it's a much better, for some of the materials, is a much more better properties at the end. The material ends up having much better properties in the end. Now, people took that welding and they're now applying it as an additive process. Can you build layer by layer using this welding technique? And they call it friction stir additive process. And people are seeing very good results. Their material that are coming out of that process have properties like forged material, which is really good properties. So I'm really excited about that technology as well. And there are folks that are also working in academia that we are hoping that we can partner with at some point, are working on robotic forging. So think of how a blacksmith hammer a piece of material into shape. People are doing that with robots now. So the robot actually look at the part, hammer it into shape incrementally, and make a very nice part that's forged. And forged material usually have the best properties, at least depending on the application. But so I'm really excited with both of these technologies that are being developed.
Amazing. Well, Ed, thank you so much for being on the show. This is great. I learned a lot. And I think you're the first.
Thanks for having us.
Yeah, you're the first. I think you're the first founder that I can say that fits into the theme of, the future of manufacturing on the show. So we appreciate you taking the time. It was a great conversation. Thanks for having us. And then, and I'm excited to continue doing the exciting things we're doing with the aerospace world. And following you, obviously, with your developments and the news that you're sharing and being the voice of the industry. Thank you, Ed. Appreciate it.